Hello, this is Mrs. Nearing, and this video will be on states of matter and intermolecular forces. Here's a review of the intermolecular forces in order from weakest to strongest. There's dispersion forces, dipole-dipole, hydrogen bonding, and ion dipole forces. Dispersion forces exist in all substances, whether they be polar or nonpolar, and they increase with increasing size. So think about your periodic trends and the size of the electron cloud. So think atomic radius. Dipole-dipole forces occur within polar molecules. Hydrogen bonding occurs within a subset of polar molecules that have a hydrogen bonded to a nitrogen, oxygen, or fluorine. That's a particularly polar bond, and that's a stronger intermolecular force there. And you can have ion dipole forces in which one of the species involved has a permanent charge. It's actually an ion, and so that ion dipole attraction will be a little bit stronger than a dipole-dipole attraction. Here's another visual showing your intermolecular forces. This is from your textbook in chapter 11. And let's talk about the states of matter and how this relates to intermolecular forces. So when we're comparing states of matter, you can see these visuals here showing the difference between them. Solids are held firmly in place but can vibrate within a limited area. So the molecules in a solid are still moving, but their movement looks more like a vibration, maybe like a wiggling in place. Liquid, the molecules in liquid can flow around one another. They're kept from flying apart by attractive forces between them. So they're still fairly attracted to their neighboring molecules. They can move around, but they're not going to move as freely as gas molecules. So molecules in a gas fly around in all directions at great speed. They're really spread out. So moving around rapidly, very spread out. Here's another picture showing the differences between them. Gases have very low density. Liquids and solids have relatively high densities. If you look down this picture on the bottom, you can get a good sense of what that would look like. So you can see gases are very much more spread out than your liquids or your solids. The strength of intermolecular forces, if you're comparing samples that are at the same temperature, that's key to keep in mind. A gas is a substance that is a gas at room temperature, for example, would have weaker intermolecular forces than a substance that's a liquid at room temperature or a solid at room temperature. So here's some examples here. We've got three molecules. They are all nonpolar molecules. So they all experience dispersion forces. But we find that at room temperature, so about 20 degrees Celsius, iodine is a solid, while bromine is a liquid and chlorine is a gas. So what that tells us is that iodine is experiencing the strongest dispersion forces. Chlorine is experiencing the weakest dispersion forces. So the substance with the stronger intermolecular forces is more likely to be a solid. The one with the weaker is more likely to be a liquid or a gas. And to think about these particular examples, what's happening here is dispersion forces increase with size. So molecules with larger electron clouds are more polarizable, so they can experience stronger dispersion forces. So that's why iodine is a solid, because it's the largest of those three molecules, experiencing relatively strong intermolecular forces due to that dispersion force. Okay, so the heat of vaporization. This is something that's measured in kilojoules per mole, and what it represents is the kilojoules of heat energy required to evaporate 1 mole of liquid, so to turn 1 mole of liquid into a gas. This is always a positive value, so it always requires energy to overcome those intermolecular forces of attraction, and molecules with stronger intermolecular forces will have higher heats of vaporization because they have greater forces to overcome, so it's going to require more energy to separate those molecules. Vapor pressure has to do with how much a liquid will evaporate. And so the way that you define vapor pressure is, imagine you put a liquid in a sealed flask. That liquid's going to evaporate, turning into a gas, until at some point the rate of vaporization equals the rate of condensation. So condensation is when your gas is turning back into a liquid. So at some point, if you let it sit for long enough, it's going to reach what we call equilibrium, where the liquid is turning into a gas at the same rate as the gas is turning back into a liquid. And if you stop at this point and measure the pressure exerted by the gas, that pressure is known as the vapor pressure of that liquid. So a molecule that evaporates really readily is going to create more gas particles bumping around, and so you're going to experience higher pressure. Liquids that don't evaporate very easily will have relatively few gas molecules bumping around, you'll have a lower pressure. So what we observe is that if a substance has strong intermolecular forces, less of the liquid will evaporate, resulting in a lower gas pressure. So that gives you a lower vapor pressure. If you have weak intermolecular forces, you have more liquid evaporating, so you'll have a higher vapor pressure. There's also a role of temperature in this. So if you increase the temperature of your liquid, you're giving your liquid molecules greater kinetic energy. So they're moving around faster, and they're more likely to have enough energy to break free of the liquid state and turn into the gas state. So you're going to have more evaporation happening at higher temperatures. So if you have more of your liquid evaporating, that means you will have higher vapor pressure. So we find there's a relationship between temperature and vapor pressure. So as temperature increases, more of the liquid evaporates and the vapor pressure will increase. And this brings us to the idea of a boiling point. So the boiling point of a substance is the temperature at which the vapor pressure reaches the atmospheric pressure. So that's the point at which we think of your sample as turning from a liquid to a gas, because that vapor pressure has reached the atmospheric pressure. Notice how the boiling point varies by substance. So depending on what intermolecular forces those substances are experiencing. We'll also find that boiling point varies with altitude. So you may have noticed that some baking recipes provide special instructions for high altitude. And that's because if you think about how our boiling point is defined, it's the temperature at which the vapor pressure of your liquid equals atmospheric pressure. So if you're at a high elevation, your atmospheric pressure is going to be lower. So if you live in Boulder, Colorado, which is where I used to live, or if you're on Mount Everest, you're going to have much lower atmospheric pressure, meaning it will take less energy. Your temperature increase will need to be less in order to get your vapor pressure to equal that point. So if you measure the boiling point of water in Boulder, Colorado, for example, it's 94 degrees Celsius. And on Mount Everest, water will boil at 70 degrees Celsius. And we can see this looking back at this graph. You can see where the intersection would be if the vapor pressure, right now this line is drawn a normal boiling point, that would be at 1 atmosphere pressure. So if that horizontal line right here dropped, and you're let's say you're down here at Mount Everest or here in Boulder, Colorado, your boiling point would drop as well. Heat of fusion is measured in units of kilojoules per mole as well, and it's the kilojoules of heat energy that's required to melt 1 mole of solid, so turning a solid into a liquid. And this is always positive, same as the heat of vaporization. It always requires energy to overcome those intermolecular forces. And a substance with stronger intermolecular forces will have higher heats of fusion. So it's going to require more energy to overcome those intermolecular attractions. So heat of vaporization was liquid to gas. Heat of fusion is solid to liquid. Then we have sublimation. So some substances can sublime, which is when they go straight from a solid to a gas, skipping the liquid phase. And one example of this you might be familiar with is dry ice. So when you put some dry ice out on the countertop at room temperature, it will go straight from solid carbon dioxide into gaseous carbon dioxide. Now we're going to look at a heating curve and see what happens at various points during a heating curve. This one's specifically for water, but similar things would happen with other substances. You would just have different melting points and boiling points depending on your substance. So step 1 during a heating curve, you have a solid and you're increasing the temperature of that solid. So the state of matter is remaining the same. It's just the temperature that's increasing. That means that the kinetic energy of the particles in your sample are increasing, and that generally means that they're moving around faster. Part 2 is a phase change from solid to liquid. This is the melting point. Notice that during the melting point, the temperature stays the same, so the temperature is flat. So you're turning, for example, in this case, you're turning from solid ice at 0 degrees into liquid water at 0 degrees. So temperature remains the same. Part 3, heating up a liquid. So again, the temperature and kinetic energy of your sample is increasing, but the state of matter is staying the same. So it's a liquid throughout all of kind of stage 3 here. Part 4, you're changing phase again from a liquid to a gas. So this is known as the boiling point. Temperature, again, remains the same during the phase change. So you're turning from liquid water at 100 degrees Celsius to gaseous water at 100 degrees Celsius. Then once all of your liquid has turned into a gas, then you're going to heat up the gas. The temperature, kinetic energy of your gas sample is increasing. The state of the matter remains the same. So that's an overview of what a heating curve looks like and what's happening during a heating curve. Looking at this graph, something you want to notice is during this solid to liquid phase change, the energy change that's occurring right here is the thing described by heat of fusion, which is that thing we just talked about, energy to change from a solid to a liquid. And then right here, this flat part, the energy change occurring here is described by the heat of vaporization. Phase diagram. So this shows us the interaction between pressure, temperature, and what the phase is. So there are substances that, like for example, nitrogen. We think of nitrogen as typically being a gas, right? But nitrogen is a gas under standard conditions at atmospheric pressure and room temperature. It's a gas. But if we change the conditions and change the pressure, change the temperature, we could change gaseous nitrogen into liquid nitrogen. And the same could be said of any of these substances. So depending on the temperature and pressure conditions, we can pretty much turn any substance into any state of matter that we would like here. And if you notice in this phase diagram, you can see that in order to get something to be a solid, we typically have to have a low temperature, relatively low temperature, and relatively high pressure. In order for something to be a gas, we have a relatively high temperature and a relatively low pressure, and liquid is somewhere in between there in the middle. Here's a phase diagram for water. You can see that if we are at 760 torr, that's 1 atmosphere, that's atmospheric pressure at sea level. Then you see that 100 degrees is the temperature at which you go from a gas to a liquid. So that's your boiling point of water at atmospheric pressure. But if the pressure changes, the boiling point of water would change. Okay, so surface tension is the tendency of liquids to minimize their surface area. Basically, it's the resistance of a liquid to spreading out. Water has a high surface tension. We'll see it beat up on a freshly waxed car. Molecules at the surface have fewer neighbors they're interacting with, and they're less stable energetically. And in order for the liquid to spread out, those interior molecules in those more stable positions would need to move to the surface. And this would require an input of energy. And how much energy input is needed is dependent on the strength of the intermolecular attraction. So surface tension decreases as intermolecular force strength decreases. Liquids with relatively strong intermolecular forces, such as water, have relatively great surface tension. Capillary action is the ability of a liquid to flow against gravity up a narrow tube. There are two forces to consider when you're thinking about capillary action. There's the cohesive forces between the molecules within the liquid, and adhesive forces are between the molecules and the surface of the tube. If the adhesive forces are greater than the cohesive forces, then what happens is the attraction to the surface will draw the liquid up the tube. And then cohesive forces within the liquid will pull along the other liquid molecules that aren't in direct contact with the surface. And the magnitude of these cohesive and adhesive forces will determine how far a liquid will or will not travel up a tube. And those forces are the intermolecular forces. Meniscus, interesting side effect of the adhesive and cohesive forces, meniscus of water. We've seen this shape happens with water when we're trying to measure volumes in graduate cylinder. Okay, then there's viscosity is our last thing we're going to define. Viscosity is the measure of a liquid's resistance to flow. So for example, maple syrup has a higher viscosity than water, and honey is another example of something that is relatively viscous. So viscosity depends on intermolecular forces. So molecules with greater intermolecular forces are more attracted together, so they won't flow as freely. And also molecular shape. So larger molecules tend to be more viscous. So there's more area to interact with and become entangled.